Okay, so hello everyone. Thank you for the invitation. My name is Lea Planquart. I'm a PhD student at the University of Brussels, and today I will speak about one specific star, V Hydrae, which has the particularity to be an AGB binary with a jet. So let me introduce a little bit the context. So as you all know, the current paradigm explains the bipolarity of planetary nebula by shaping mechanism from binary interaction. However, we have a lack of observational evidence for binary among the progenitor. By observational evidence, I mean direct evidence of their orbital period or the eccentricity of the orbital parameter. And this is mainly due to the brightness of the AGB and its variability, making usual detection technique a little bit complicated. So in this work, we decided to study the best candidate to assess the binarity, which is the carbon star V Hydrae. Why is it the best candidate? Mainly because it's a suspected AGB binary, and the suspicion comes from the presence of a UV excess, which is not common for a carbon star, and a long variation in the light curve. So here on the right panel, you have the light curve in the visible, and you can see long variation on the top of the short variation. So the short variation are due to pulsation that are about 500 days, and you have long of 17-year variation in the visible, causing up to 3 magnitude dimming. Also, it's the best candidate for this transition AGB to planetary nebula because the star already exhibits quite some asymmetry in the radio range. So it was mapped, for example, with ALMA, and the idea of the general system outflow is the presence of a dense equatorial ring and high velocity bipolar outflow seen in the CO line, which is less dense, and the presence of ejection. So the idea here is to assess the presence of not of this companion by a multi-instrumental study, first from temporal constraint and then with spatial constraint. These two way of seeing the system is because we will be based on two observational data sets. So on one side, the star was observed with Hermes Mercator, so the spectrograph on the Mercator telescope at La Palma, for more than 10 years of observation. So we have monitoring radial velocity and spectral monitoring of the star, which can give us access to the temporal evolution and the Z and T coordinate of the system. On the other side, the star was also observed with Matisse infrared interferometer from ESO 2 years ago as part of the BIN AGB program. And the idea is to reconstruct an image from those interferometric observations and hence to have access to the X and Y coordinate of the system. So combining with two sets of observations can give us constraint on the four-dimensional space at the innermost scale around the system. So let me look first at the spectral monitoring. So thanks to this long monitoring, we were able to disentangle the radial velocity shift due to the pulsation, because since the star is pulsating, the envelope contract and expand, and this induces shift in the radial velocity. So we were able to clean those pulsations from the orbits. So here you have the plot of the radial velocity, and you can see that we have two variations, a short one at exactly the pulsation period, and the long one that is compatible with the dimming event periodicity. Combining radial velocity with, I was saying that we combine radial velocity with proper motion, and combining those two sets of observation, we can have access to the full set of orbital parameters. So what you can see here is that the period is exactly equal to the light curve modulation, meaning that the dimming happens exactly at the same orbital phase. And more precisely, the 3 magnitude dimming event occur when the companion is in front of V Hydrae. Its companion from the mass estimation is likely to be a main sequence star, and we have a slight degeneration in the rotation direction. So now that we have the radial velocity and the orbital parameter, we can look at binary interaction signature in the spectrum of the star. And in fact, we have one line, the sodium doublet, that is varying with this orbital phase. And the variation is that induce a blue shifted absorption that is modulated with the phase. This kind of blue shifted absorption are commonly seen in H-alpha line of post-AGB binaries. And one model by Bolen works of or Tone Duprin's work. So the idea, I'll try to explain a little bit the data, is that you have different absorption features. So you can see that superior conjunction. So when the companion is in front of V Hydrae, we have absorption really highly blue shifted up to minus 20 kilometers per second. And at the opposite phase, you will have slower velocity for the absorption. And this gives this kind of profile depending on the orbital phase. And so using the same spatio-kinematic modeling as for post-AGB, which means that the gas is located in a conical jet attached to the companion, we are able to reproduce this feature and obtain the jet parameter for this companion. So that's the view that we have on the system. We have an AGB star orbiting around a companion, and this companion launch a jet. And this jet, so in the optical, we see the blue lobe in absorption, but by symmetry argument, we can say that we also have a redshifted counterpart that we don't see in the spectra because there is no absorption since it doesn't cross the line of sight. The jet is quite open, 65 degrees, and the maximum velocity is up to 200 kilometers per second. So that's what you see in the optical with the temporal evolution. And in fact, there is quite a good match with what we see in ALMA. So in ALMA, we have this dense equatorial plane in low velocity, but at high velocity, we have a bipolar jet. And the orientation and the velocity of these jets are compatible with what we see in the optical at really the innermost scale. So this gives us really strong constraint on the gas distribution of this system. But gas itself cannot explain the dimming event that are broadband, and I speak about this 3 magnitude modulation with the orbital phase. So there must be something occurring with dust, because only dust could explain those long observations at the superior conjunction. So to locate the dust in the system, we use the interferometric observable obtained with MATIS and reconstruct images in the L and in the N band. So the 2 infrared, thermal infrared band, so from 3 to 12 micron. With interferometry, we are able to have spatial resolution up to 3 milliarc seconds, not 8 milliarc seconds, and hence, given the parallax of the star, we are able to resolve the surface of the star. So on the left panel, you have the L-band image. So in the nearest near infrared, at two snapshots at 2 different positions, one in molecular absorption and one in the pseudo-continuum. The first thing that you can see is that we have only one central object, but that this object is not spherical at all, not circular. And here you can see that the brightness distribution lies within the expected radius of the star. So we have presence of opacity effect maybe that change the shape of the star, or the presence of convection cell on the stellar surface that made those asymmetry. On the right panel, you have the N-band images. So further in the near infrared, so further in the dust emission, and you have 2 images, one in the amorphous carbon emission feature for continuum, and one in the silicate carbon emission. And what we can see is that here the stars look brighter, and we have emission with an extension on the northeast part. So this could be interesting because it's outside the expected radius of the star. So let's take a look further to this one. It's the same image, but with a more spectral bandwidth to reproduce it, and with some contour line to highlight the elongation that we have for this star. So we have a central object and a northeast elongation that made the star look a little bit like an avocado. So if we compare the star with the expected position of the companion, since we have the full orbital parameter, we can see that the companion, I said that we had the degeneracy on the rotation axis, but for one of the solution, the position of the compatible at the time of the observation is compatible with Matisse observation, meaning that this dusty clump that we can see on the image could be linked with the motion of the companion. Additionally, we look at archive data, and we had a change in the morphology with respect to the media observation taken more than 10 years ago. So the star that we see here was not looking like that 10 years ago. So this is further evident that this northeast clump is related to the presence of enhanced particles surrounding the companion. We don't see directly the companion, it is unresolved, but we see enhancements of dust particle in probably dust particle around this companion. So to sum up all the observation of this star, so we have at the large scale the ALMA image with 6 concentric rings that are spaced by several hundred of astronomical units, hence time evolution done more than 100 to 1,000 years of creation. And if we look at the innermost part of this ring and in the infrared, we have the visual coronagraphic image that are quite a little bit boring, so really circular. The dust at that scale is really spherical or circular distributed. And if we go in the innermost part of this circular dusty shell, we have the Matisse image, where we can see the AGB a little bit distorted around its surface, and an asymmetric giant blob located at the expected position of the companion. So we have asymmetry from large scale to small scale, and we prove that there is probably a companion that is the main cause of all this asymmetry. So to summarize the result from the orbit and the gas, so from the spectral monitoring, we resolved the orbit and we found the presence of a conical jet that is orbiting around the system and attached to the companion. And this is consistent with the large-scale hourglass shape that we can see. And on the second part, from the mid-infrared image, we have detection of asymmetry, and those asymmetry could be interpreted as dust particle enhancement around the unresolved companion. This altogether gave further evidence that binary interaction shape the bipolar shape of V Hydrae and maybe on other late AGB star. So yeah, for the next part of this star would be, of course, to really understand how this light curve dimming happens, so how this enhancement of particle around the companion could create the shape of the light that we see, and what is the 3D structure of the dust clamp and how is it located within the jet. So for that, we need further 3D modeling and phase-dependent dust distribution, because we only have one snapshot taken with Matisse, and it would be really interesting to have the dynamical or the evolution of this dust clump with the orbital phase. So that's all for me. If you have any question, I would be really glad to answer you, and I hope there were no other cut in the presentation.
I'm sorry, I'm asking too many questions. So this is really interesting, because in my talk, I had taken V Hydrae as a possible post-common envelope counterpart to the extreme carbon star. So this would have been an oxygen-rich one with extreme dust. However, this orbit implies an so 17 years in this system is what, about 5 AU or so? It's like Jupiter.
The separation is about 10 AU.
Okay, like it's a handful of AUs. So this implies a more distant binary interaction, right? So this is like a Windrush lobe overflow or wind interaction, which is absolutely fine. But you're probably showing also that there's extra dust production in this type of interactions. So it's not just the common envelopes that may make more dust, but also these. And this has really got implications. There's been a lot of talks today and the past days about this very dusty objects that may not be explained with single stars. So the question is, how do we explain them with binaries? And now I think we're starting to see different methods in binaries that make dust likely in different ways, but they're all quite copious. So there's a lot of dust. So that's sorry, this was not really a question, was it? It was more a comment, but it's a really fantastic work and also interesting to see the jets, just like in the post-AGBs.
Yeah, I mean, thank you very, very much.
Find more. We need more.
Yeah, exactly. That would be the best conclusion. We need more of this system to have a better idea of the parameter space of those orbital parameters.
Lea, a question. V Hydrae is also the star where I think also Sahai have seen these bullets, or how he might have called it. How do you link that to your current results?
Yes, exactly. So I didn't mention in detail the bullet, but there are in the sketch here at the introduction, you can see the blue and the red. The blue and the red bullet here on the sketch represent the position of those bullets. So the bullet that Sahai see are enhanced density in forbidden line in the UV, so it's sulfur doubly ionized. And what we have is that the location, the orientation of our jet is consistent with those bullets. So what I show you here, this bipolar jet, this would mean that the bullets are located within the axis of the jet, so somewhere here. The fact that it is forbidden line means that we need a low. Sorry, it's only to me that this thing happened, or maybe
Yes,
that's
it's yours.
Okay. So what I wanted to say is that the bullet should be located in the cavity of the jet because of their low density. They should be located in the axis of the jet, and this is compatible with the presence of a cavity in those jets. But yeah, those bullets are really huge, so they are several times the size of the orbital separation. So the question is how they can be formed.
Yeah.
But,
okay, I would love to know that question.